All right, so we'll just get started. I've heard a couple of, apparently our bus system continues to be the exemplary system for getting students late to class. One student's like, I've been here since 8:30 and it's 9:15. I can't blame that one on you. But the thing I wanted to do is we went over 5.11. We went over it pretty quickly last class. I did want you guys to give it a shot, but I wanted to go over it step by step because there will be a similar problem to this on your exam. So I want to make sure that you thoroughly understand this. Additionally, I think this problem covers pretty much every pointer-related concept. If you understand this problem really well, then you'll really get pointers, right? So one thing I want to have open is I want to make sure we have this, the lecture 5 notes here, because that has our TGO with our this one. Right. Yes, Brian.
Is there any way when we go through the assembly language we could have the higher order language side by side with it?
What do you mean the higher order? Oh, I mean
these two windows next to each other.
Sure, we can try this. And then let's just create a new, you can go away, new. We'll move this over here. How about that? Is that good?
Yeah.
All right, perfect. All right, so let me do my little page layout right. Okay, so what we're doing here is we want to kind of compare this code and our problem statement and kind of look over what I mean when I'm asking this question. So let's go through each one. So translate the following C code into MIPS. So we're going to be using I will have a copy of the MIPS screen sheet available and printed out on your exam, so you'll have that available to you. Array, so is an integer array of words allocated in main, where the base pointer to array is S0. So what we can say right here, I'm going to okay, so array pointer is S0. Right, just make a little note up here. And then going back, so first is S1. So if we look at the code, you can see that first is an integer, and then second is S2. So we can do some commenting here at the beginning. In assembly language, the commenting is dash dash, so you can say pointer to, oh, that font's going to be still a little too big. Let's do 9. Pointer to array is S0. First is S1, and then second is S2. And then we can go back in here, and then sum is S3. The initial instruction is that, I'm going to change that to 1 to explain why. So technically, the initial instruction is at S0, but I want you to understand the concept of what return 0 actually is. So you may assume all register values are initialized to 0. So it'd be like if you were writing in code and you were doing calc. So that means we don't have to initialize first. On an exam, I will probably, you may assume that all register values are initialized as stated in the code. So here's what I mean by that. So this is the wording that you'll see on the exam. So here we have our function initialization. Array of 7-element array, 10, 2, 3, 5, 4, 0, 5. What this means is that I've told you that there's a data memory element where we have 7 elements. Well, so we'll call 0 is our base pointer, or whatever S0 happens to be. Whatever that value is, it's going to have these 7 elements there already, because it's a. And we admit, now, let me ask you a question. Why is that a fair assumption to make? Why am I allowed to make that as a fair assumption on an exam? Think back to the basic definition and philosophy of MIPS. MIPS is a what-driven what of the what? Encoding of the microengine, right? So your compiler is going to load all this stuff into the memory for you. So if you want to know how that's done, you can take a compiler design course. So this is a little outside the scope of advanced digital systems. So we have loaded first and second, but you'll be doing this in your code. You'll be actually reading in from file and putting that into registers in the data memory and instruction memory. So you'll be kind of simulating that. It's much more complex than a compiler, but you'll get the general idea. So you've started your function, you've read everything in from the file, you put these elements into data memory, and you put first and second into S1 and S2. And sum is initialized to 0. Right? So all the other ones are initialized to 0. Now we're going to call test functions. Array, we're going to have a pointer to first in the function, and then we're going to pass second by value. So this is where we're going to start our code. Basically, this assume all register values are initialized as stated means you don't have to worry about writing this on the exam. That is meant to save you time, I promise. So our first thing we're going to do is we have to worry about getting the values to the function, right? So instruction 1, we're going to go in order of operation. A0 is the pointer to array. So there's multiple ways we can do this. So what are the variables that you can use for arguments in a function? Remember from your MIPS screen sheet.
A0 to
Bingo. We have 3 available to us, right? Taking A0 to A3. So we have 4, but all we will need is 3. So this is where you are actually physically creating a pointer. In order to pass the function, we have to have this array. So what we're going to do, we can do 2 things. I'm going to show you both of them, and either one of them will work sufficiently on the exam. You can do add I, and then that tab went a little too far. But so we'll call this A0 because that's our first argument. And then the pointer is S0, right? So we are going to put the value of the pointer in memory into A0. And going back to where we were before, so A0. And so this means we're going to add S0 and then the value 0 because we don't want to add anything to it. There's a second way we can do this. Is there any register in MIPS where we can represent the number 0? The 0 register. Very good. So we can do this as well. We can do add. So this is an R-type instruction instead of an I-type instruction. 0. And so we have now created a pointer in the function that creates the pointer to array. That's our first instruction. And so we'll just say pointer to S0. So the second instruction, now we're going to deal with, we have our star first in our function call, and we have ampersand first to call our function, right? So what is the value? What are we going to do here? So I want to read a portion of this question that pertains to this. This is specifically for dealing with pointers. So, not what I want to do. I want to do this one. There we go. you may load any pointer to an integer to locations in data memory. Let me make this a little more clear. So you may load to any location data memory as long as you properly load and store it. So we assume that S0, that all the values are loaded as 0, right? So we can say that S0 is at 0. So if we say that S0 is at 0, and that means 0 through 3, 4 through 7, those take the first 7. So 0 through 28, 29, 30, 31. That means the first element available to us is 32, 33, 34, and 35. So you can load the value of first into data memory. So you have to create this pointer, and the location has to be put into A1. So here's how we do this, right? So you can say store word. So we're going to take the value from S1, and then we're going to have 8 because we have 7 elements in array, right? And then we'll just say S0. Now what that means is there have been 7 elements in S0, and we're going to take that 8th element, which is the first free element after the array, and use that to place our pass by reference value for first. And so now I've stored it in there, and now I'm going to do add. So now it's A1, right? A1 is going to be our pointer to this location. So the way we do this is simple. We just do S0, because that's where we were, and then 8, because now we 32. Why did I do 32 here? Actually, some of you should have called me out and said, Professor Morrison, you're wrong. That should be 32. Right? Professor Morrison screwed up. Nice one, Doc. So that's 32. So now we have the location in memory. I've taken that value, S1, that is first, stored it in data memory, and now I've said A1, tell me exactly where that is in data memory. So now we have created a pass by reference value in A1. And so A2 is going to be second, right? Now we're passing by value. So this just becomes add A2, second is S2, 0. So that any change in A2 in the function will not be affected by what we do. Any change that happens in the function to be passed by value second will not change the value in main. So this is a pass by reference. This is pass by value. This is the array. So the next thing, now that we have done all of this, we're going to do some sort of jump, right? We have to jump down here. So we're going to call this here. And so what we need to do is we need to say, we have to write the rest of the code for this first because we need to know how much we have to jump by, right? So right now we're going to leave this blank. This is kind of one of the reasons why I wanted to work through this problem slower, you understand. So basically come the tricks. How did I come up with jump? How did I come up with this branch number? How did I come up with all this? So we have this jump value. And so what's going to happen is a bunch of things going to happen in this code that we're going to jump to. And the result we see here at int, we're going to say that v0 is going to be our result. because that's one of our return registers. When you call a function, you can put it in v0 and it will work. So, since we know sum happens to be S3, our next function can be simply, there's one thing we need to do. Jump return. And we're going to do add immediate here. So we're going to do add immediate. And so what is RA? Return address. So we need to tell where the function needs to go back to. Right? So then we're going to tell this number to jump here, jump past, and then we're going to have this next number. So this is going to be changed to 6. And then that means we're going to have 0 here, and then we're going to jump to instruction 7. Because what's going to happen is the function is going to be called, and then this next instruction that we're going to have here, that's what the next thing is going to happen after we're done with the function. So we then say instruction 7. So we're going to leave this blank for the time being because we don't know exactly how many instructions we. So instruction 7. So the jump return puts us back at 7. The next thing we're going to do is we need to take that value from v0 and load it into sum. So we're going to add v0 S3 v0 and 0. So what we're going to discover is in this function that we're going to call here, every time we update the pointer to a0, we're going to be storing it back into memory, right? So the next thing to do to close this pointer by reference is to take the value from that data memory that we've been updating the whole time in the function and update S1. So we passed by reference, we did a bunch of stuff, and the last thing we need to do is we need to do a load instruction. So this simply becomes, instead of doing this, because it's a similar format, we make it 8, and we do load word. So we're taking that 8th element in memory that we allocated and storing it back into S1. So that is how a pointer by reference happens. We start here, we take that value from the register, we put it in the data memory. Every time we do something in the function, we update it, update it. When we get done with the function, the first thing we do is we do this load word instruction, and that allows us to be able to close the pointer and have the most updated value. And that is why when you do this, where you do the ampersand first, and then you do everything, and you test this, and you can see the sum plus first plus second. In this code, we're updating first value. But here's the thing, we're also updating second, but it's not going to change because we're not going to do anything. So now we have our sum updated, and we now have first updated. So 9, we have to start here. And so that should have been, let me close that out so we can have that side by side again. And so the first thing we're going to do, we have to add sum in first. And so we can use a temporary register. And then we can add, I'm sorry? No. Why not? This is a good point. I want to hit on why not S3?
Because S3 has a V0 in it
No.
now.
We've gotten 3.0. We have to put it in S3. What's this value that I just did?
A temporary register.
Temporary register. Why did I use a temporary register here? Let's go back. This goes back to why Brian wanted this up. So let's analyze this line of code, which is what we're doing. I want to do sum plus first. And then what do I want to do?
You want to add add that for second. Registered that.
Yeah, remember in MIPS, in the architect, and this is why it's important to understand the architecture and why advanced digital system is important. This really ties into the meaning of the course. In a CISC architecture, you could create an LU that does 3 additions. Your constraint in the ALU, which you all designed, is that you have 2 inputs and 1 output. So you have to add them 2 at a time. So, but here's the thing. This is where the mistake comes into play. You may not do this. You cannot do, let's see, which one's second? Second is S2, right? You cannot do sum is S3 and first is S1. Why is that wrong? Why is that minus points?
You don't want to override your S2.
Why? What are you saying, Xavier?
You don't give the instructions to do
You never tell the code to do that, right? You never say at any point second equals sum plus first, right? So we have to create a temporary register to hold that value, and then temporary plus second becomes the sum of second. So, but that's a really good question, though. It's important to work through these things. So this becomes, instead of S2, we're going to use one of our temporary registers to hold that value. And then our next instruction will be, and let me, because I'm somewhat OCD about these things, and it'll help you see it much better. And then we add, and then this is going to become second, which is S2. And then we're going to add the temporary register, and then we're going to add second, which is S2. So that maintains our order of operations and maintains what we call cache coherency, which we'll go over a lot more in section 7. Yes?
Dr. Morrison, that's what I was saying. I was saying S3 would be the next thing you were going to type out.
Oh! Oh, I thought you were telling me that I was supposed to... No, you were correct.
Okay.
No, you're right. In that case, I just spent a whole lot of time. But forgive me, I apologize, but I should note that that is a very common exam mistake. So in a weird way, you kind of helped everybody. Hopefully, by doing that, we all raised some. We hope somebody got a better score on the exam because of that. But I apologize. So in that case, so now we have added. We now have our sum value. Second value. And then this last thing we're going to do jump 0. And later in the course, we will learn what happens in this instruction 0. And so what does this mean we're going to do? So this is where our function is going to begin. We can start our function here. But before we write any of our function code, what should we do?
Jump to
Okay. So jump to 12. Now, the reason why we don't multiply 12 and jump, when we get to the underlying architecture, which we'll get in 2 seconds, we're almost there, is that here you have to actually multiply by 4 in the architecture, where in branching and jumping, there are actually shift left logicals hard-coded into the hardware that will do that for you. So jump and branch don't multiply. Load and forward do multiply. Does that make sense? I hope that's clarified. Before I go any further, I know the buses were a nightmare, so I think Tony McKinnon and Christian came in. So if you guys would like to turn in your homework. Yeah. I was emailed by multiple people that the buses are a nightmare, so if you want to. So is this, while they're turning it in, is everybody understanding this so far? Does anybody have any questions?
So your instruction 2, you are loading your
Storing
your
S1 into the 8-bit array.
Not 8. No, not 8. That's a good question though. So what we're doing here is we have some registers here, and then some magic happens. We have the ALU does some things. Then we have this data memory, big block of data memory, right? So what we're saying is the first 7 blocks are held up by the array, right? And so by my problem assumption, you can put it anywhere else. You could put 32, 36, as long as 40, whatever you want, as long as you're consistent throughout the problem. Like if you put 40 here and you put 32 here, you'll lose points because your code you'll grab gibberish. Does that make sense? So what we're doing is we have this block for the array, and then we're putting it in the next block. All right. So now we've jumped to 12. So now we're here. So we have our values. We have in array pointer. We have our first, which is we have a pointer to first here. So the first thing we need to do is we have a pointer to first, but we don't actually have the actual value of first. So now we need to do a load word operation here. So we're going to load word, and I'm going to call this temporary 0. So I'm going to make a little comment over here. T0 is first, or star first. That'll make it easier, right? So T0. And now A1 is pointing directly to where we want it to in memory, right? Because in this instruction here, up here at N2, which Joseph was just asking about, we added 32 to the base pointer of S0 to put in A1 here, right? So now, but A1 is pointing directly to where we want it to go. So what should the number be in front of the load word here?
0.
0, absolutely right. And then we'll call this A1, because that's, so here I put a little comment, T0 is start first. So now we have passed by reference. We now have in T0 our local copy of first. And so here, int sum equals 0. We are calling that V0. We can assume, based on the problem, that all values are initialized to 0, right? What would I have? So that's why in the assignment we didn't have anything. But let's say I changed it to this. Let's say I was being malevolent and I changed it to a 1. What do I need to do there? Let's see if you guys remember. Let's see if I'm asking somewhat of a trick question. Think to what I was kind of, a blank is a blank of a blank, right? Think back to that. What's the philosophy, main idea of MIPS, all that stuff? Yep, compiler driven. Yeah, there we go, right? So you can do one of two things. You can either assume that we stored it in V1, because it is compiling. The compiler will go through the entire code, as you guys know now. And V1 will initialize to 1. But you can say that, that's fine. Or if for some reason that wasn't there, and you typically want it to be there, you could do 13 add V0. You want to do add I. V0 0 and 1. You do that, but I want you to assume it because it's compiler-driven encoding of the micro engine, so don't do anything. So it's there. It's in V1. All right, so now we have this little while array first does not equal 0 bit. So remember from the previous class what we had to do when we have a value stored in a register. What do we have to do here?
Branch.
No. Before we branch, this is dealing with. I'm asking specifically about this. Before we can branch, we need to know what that value is. Yes. And what's the simple way to multiply by 4? Shift left logical, right? So what we're going to do is we're going to take this T0 that we just did. We do shift left logical, and we can do T1, T0, and 2. So T1 equals T0 times, or you can even say star first times 4, right? And so we know the base pointer of array is an A1, is an A0, right? So we still don't have a point where we have a number, right? We still have it in a register. So what was that second instruction that you have to do here? I know the offset is in T1, and the base pointer is in A0. Where do I find the exact location in memory? Base pointer, and I know my offset. Starts with an A. It's an arithmetic instruction that starts with an A. Addition. I want you to add, right? So the second thing I want you to do is you're going to do add, and we can reuse T1 because the value is no longer necessary, right? T1, and we're going to add A0 because that's our pointer to our array, and T1, which is our offset. So that's array of first there. So that's a pointer to, when I spell array right. Okay, does that make sense? So now we're pointing to what we need. And then the last thing we can do is we can say load word, and we can use T1 again. Actually, let's not use T1 again because tricks of the no, we can use T1 again. That's fine. We'll use T1 again because down here, see we have array of first. We're going to use this value again. So T1 is now going to contain array of first. And what's the number I'm going to put in there since I'm pointing to the exact location? 0. Very good. And since T1 has the original pointer, I'm now taking that and I'm now putting the exact value in there. So now, Joseph, what do I want to do? Now that I have this value and I have that value, what do I want to do?
Branch.
I do want to branch. Now, it's what array first does not equal 0, so what instruction would I like to use? Branch equals, right? Because it's the exact opposite. So, since it happens to be 0, we can do a neat little trick. So I do branch equivalent, T1, and we just say 0, and then we're going to leave this value blank for the time being because I need to know how many instructions are going to take me to get there, right? So we'll get back to this. Okay, so now we are inside here. So now we have star first is less than or equal to second. So this is where your TGO comes in. Section 5 lecture notes. If I is less than or equal to j, you want to set less than. Let me get up the Word document version of this because then I can just copy and paste it. Right. So if it's I less than j, that means we're branching if j is less than I. So we have this assumption T0 and T2. So I'm going to copy this, and then I'm going to show you what I mean here. Okay, so our next instruction is set less than. So we're not going to call this T0, we're going to call this T2, right? And with the two, so S2 is the one on the right and S1 is the one on the left. So in this case, going back to our function, we get rid of this. We get rid of this. First is on the left and second is on the right. So second is in A2. So we're going to put this here. And first is this one here. And we currently have first, the value of first is in T0, right? And so we're going to set T2 to 1 if second is less than first. Right? And then, so it should be 1 if we want to get in there. So it should be 1 if we don't want to get in there. So that's why we're going to branch not equal T0. This will be, we're going to change this to T2 because that's the actual one. So that means it's 1 if we want to branch for the set less than. Because we want to meet this condition. Right? So that if it's 1, then we go to branch if not equal, T2, 0, and then we will cut back here in a moment. So we have a couple more blank spots. For the time being. So let me, I'm going to press enter a few times so those of you in the back can start seeing what we're working on. All right, so we now have gotten past here. So now we need to do this, right? You do this instruction. We've passed our while loop, we've passed our force loop, and now we are inside here to do our sum instruction. So sum plus equals is going to be sum equals sum plus array of first. So do we have array of first already called? Yeah, we have it T0, right? No, it's yeah, T0 right there, right? So what we can do, instead of having to do load word and a store word again, you can just do 19, add, and so sum is V0, right? And we're going to add the current value of V0 and T of 0. And that's this guy here. All right, so now we're at instruction 20. So we've done this, but here's the thing. We wanted to branch past 19 if this condition wasn't met, right? So we want to get to 20. Now here's the way the architecture works, and in section 7 we'll go into this in tremendous amounts of detail. But right now, just understand that this is what happens. When the value comes out of the program counter, the current instruction, 18, right? What's going to happen is the first thing that happens is it's incremented PC plus 4. So basically what happens is it's a value, 18 is multiplied by 4 intuitively in the architecture. Then we add 4, and then we add the value. But here's the way you can represent it in it, because the branch value that you have in there is also shifted left by 2. So you're multiplying it by 4. So here you don't want to do that. So here's what we're going to do. You start with the instruction that you're currently at. So you 18 plus 1, because you're automatically incrementing by 1, which is the same thing as adding 4 in the architecture, plus, and then you take the number where you want to get to. So I want to get to 20. So I have 18 and 19, and then just add the difference. And you'll see a lot, when we go back to do instruction 16, this will actually become a little more clear. So 18 plus 1 gets me where I want to go. Now, the last part is you take that out. Now, here's why. I'm going to kind of go give you a preview. So you have something come out of PC, goes into a small adder. This is why I had you do a separate adder, hard-coded 4. The value comes out. We got here, and then at the same time, what's coming out of the instruction is the 16-bit value. It's shifted, it's sign extended by 16 bits, so now it's a 32-bit value. And then what's going to happen is shift left 2. So now the value that's coming out here, 2, becomes 32-bit, and then it's multiplied by 4, so now it's 8. And then it goes to yet a second adder. And they come back out and go back to the instruction memory. So this value that comes out here is 18 times 4. It's added here. And then you're going to get 8, which is representative of 2. So you're going to have 8 plus this value is going to be your next instruction, which is going to be 80. By the way, our hardware architecture works. But we'll go into that in section 8. But for now, that's how it works. But that's my little trick that I did when I took this course. Is I would go 18 plus 1. Okay, so now I need to get rid of all that. Feel free if you got it, because you're going to be where you're at. You just go, okay, the first thing I want to do, I want to skip over this, plus I want to get one more. That's sufficient on an exam. So now we're at instruction 20. Instruction 20 is this first equals first plus 1. So the first thing is pretty intuitive. We're just going to add I, T0, T0, and 1. But what do you think the next thing we're going to do here is? We've
stored T0 in originally what first was.
Yeah, exactly right. Why? What is star first? That's passed by. Correct. So anytime you update a value that's passed by reference, so you have to store it back in the data memory. So everybody, all of it, you were kind of raising your hand, and Joseph beat you to it. It's all right. That is exactly why. So we're going to do a store word instruction, and oh hey, look what? We've already done that. So you can just, when you do it on the exam, or quiz or exam, you can just do that. Just rewrite it. Don't cause yourself any trouble. So let me scroll down for those of you in the back. You see what I'm saying here? What I've done? I've incremented the value that's stored in T of 0, which we currently have the pointer to first, and then we store it back in data memory. And the reason why we do that is because when we get back here, you see at instruction 8, when we load it, we've now loaded everything that we've changed into first back into data memory. And back into the registers, sorry. So we are almost there. So we're at instruction 22. I've added, we've gone through all this. I don't know why it's not working, but oh, the color is now, yeah, there we go. So now we're here, and we've just done that. We've done our proper storing, and now we're here. So the thing we need to worry about is we're going to jump back to our function, right? So we're done with JR, and we've stored RA there, right? So that's jump return. But if we don't meet this condition, that's where we want to jump, right? So we want to jump to 22. And so we're currently at 16. So we want to jump how many? We want to jump 16, 17, 18, 19, 20, 21. We want to go to 22, right? So then we have the plus 1 because it's automatically hard-coded, which is 5. So I will accept either of these on exam. If you go back here, you can do 1 plus 5, that's perfectly acceptable. If you do 6, that's fine as well. I'm sorry, 5. Because it's the plus 1's already in there. So that means this one should actually be 1. Okay, so now we jump back. RA contains the value 11. So it contains 12, right? We did this properly. Make sure there's RA. Let me do RA. We added RA. Jump. Oh no, it was up a little earlier, right? I want to make sure I did this proper before I send you on. Yeah. So then we actually have it as 7. So we jump back here. Back there. So we do this, we do RA, we jump down to 12, we do the function, and we get here, we jump back to 7, we do the rest of the code, and then we jump to 0 to end the function. So that is, at the assembly level, how MIPS, how C instruction works physically. That's how pointers work. So that's how you're pointer passing an array. That's pointer passed by reference, and we have a variable passed by value. Yes, Jeff?
Now on step 21, you want to put the value of your first. You want to put the value of the pointer in first, right?
At step 21, we are taking our local copy of T0. It should be T0.
Yeah.
Yeah. Yes. Yeah. It's typo. Oh no, that should be S0, and then S1. Right? Or you can do 0, S1. That's more appropriate for that. So here, since the local copy is stored in A1, the local copy is stored in A1. A1 is pointing exactly to where it is in memory. And we're taking our value of T0 and putting it in A1. Yes?
So what happened to V0? Because that's where...
Oh, well, V0 is updated every time here, right?
Yeah.
And so what we did earlier in this instruction...
Oh, okay.
Yeah. So that's a very good question. Okay. So what we did in instruction 7 is we took our return value, added 0, and then put it in S3, which is our local copy that we were returning in this instruction. So sum was S3.
Okay.
Yes.
And I'm guessing like in the braces and the semicolon, that's hard coded into.
That is C code.
Yeah.
Yes, that's C code. Okay. Any other questions? All right. Thank you. So so now we've gone through and we've done 511, and you guys now understand how to do all this. So next, what we're going to do in section 6 is we're going to start talking about memory hierarchies. What is this load word and store word? What does this actually mean? Why is this beneficial to us? And how do we need to use this when we implement the actual architecture? So this is the last section before we actually start getting into MIPS. So if you recall from TGO 1.25, I was talking about this data may only be stored in a local register or with load store operations, as we have demonstrated in the last problem. Repeated use of registers in a basic block of code prevent redundant load stores. So the only time we needed to use those load stores is when we were doing pointers. So more options directly related to the computation can be performed. So we have these local copies of the registers. We do all this R-type instructions with ALUs, and then we load it into the data memory to go into the memory hierarchy. So the first thing I want to discuss is I kind of throw these ideas of memories and registers out, but I wanted to make sure that you guys understood the difference and what's going on in the physical architecture. Access to registers is faster. So what that means is when you do an instruction and you have a register in the instruction, it just goes straight to the register, right, and gets the value. Whereas if I have to go to data memory, I have to go to a register that contains the pointer, I have to perform an arithmetic operation, and then I can go there provided the control signals to the data memory allow me to read or write from the data memory. As you now know, arithmetic operations in MIPS use registers, not memory. As you also know, MIPS has 32 registers. In the data path you're going to design, the data memory contains, 512 bytes. And we're going to talk about byte addressing here in a second. As a result, when we start getting into pipelining in section 7, this pipeline is this idea where we're trying to use multiple stages simultaneously to try to improve throughput. And by using the registers, we can actually result in fewer pipelining delays by dealing with these things called hazards. And then, as I mentioned ad nauseum, registers are dual read, single write. And lastly, memory is single read, single write SRAM. So I hopefully have hammered this concept of byte addressing into you by now, where it means an index points to a byte, 8 bits of memory. And so we have to use the 8 times 4 because we're actually getting 4 blocks from the data memory and returning it. The reason I hammer it so much is because when I was a teaching assistant the first time I taught this course, now almost 6 years ago, they asked a byte addressing related question on the exam, and only a third of the class got it. So I vowed when I taught this class someday that I was like, byte addressing, because that's how the architecture friggin' works. And if you don't understand byte addressing, then you're not going to understand an advanced digital system. So byte addressing means that an index points to a byte, 8 bits of memory. All right, so 6.3, you're going to see this problem again. 6.3 here. So 6.3 is giving me the 5 types of memory addressing in MIPS. And so there's the section in the book. For those of you who have the textbook, do know that I correspond my sections to, it has the exact same title in the textbook, if it's in the textbook. In this case, large and fast memory hierarchy is chapter 5. And I've split section 6 and section 8 are chapter 5 split in half. But section 6 is going to have section 7 is going to have chapter 4. But the book does a good job of describing this. So an immediate, which you're already familiar with, is an operand is constant within the instruction itself. So now you know what load word and store word instructions are. So you have RS, which is your pointer, and then I'm going to the base pointer to where you're trying to get. The immediate is your offset, and then you're storing the result in RT. So it's constant within the instruction itself. So this is an actual machine instruction, which you have some familiarity with now. 2, register. The operand is a register. So here, I've given you a hint. So you guys have done 5 to 32 decoders, right? Or no, you're going to do that next time. So what you're going to do is you're going to take this 5-bit value from your register. You're going to have it go through a 5 to 32 decoder. And then you're going to get a 32-bit value out where you're using one-hot encoding. And that one-hot encoding will tell you which register you're going to use, which operand to use. So this is exactly how to code it, right here. And so you can, in 5 to 32, you can do dash 32 there. So base addressing, and this is kind of where we're talking about load word and store word. So this is kind of physically how this is being done. So I have my base pointer to the array. I have my 5 to 32 decoder, and I get the value from register, right? Now, I actually drew this exact diagram up for you a little earlier. And then the immediate value is the last 16 bits of the instruction. So I have opcode, RS, RT, and RD. So this base addressing is taking the base pointer of the array and the offset and getting a location in data memory. We define it formally as the operand is at the memory location whose address is the sum of a register and a constant in the instruction. So here's what's physically going on when you're doing a pointer. You have a 32-bit instruction. So this 5 bits, remember we decode it to a 32-bit 1-hot value. The 1-hot value tells me which one to read. And once I get the value that I've read, this register here, what we do with this immediate is a 16-bit. And what we do is this thing called sign extend. It reads the most significant bit and just puts on 16 more bits. So either it starts with a 0, like in the last problem we had 5 as one of the values. It just 16 bits and it ends with 101, right? So the most significant bit is 0, so it's just going to add 16 more zeros, so it's a 32-bit instruction, which we need to have for the inputs to our ALU. So what's going to happen is we have a 32-bit output. The 32-bit value coming out of the register. They go into your ALU, which has an adder. It's going to actually bring in the add opcode, right? The 4-bit value that you put in. And then it goes to data memory. This value here is your base pointer and your offset. So that's your actual offset. So that's what's physically going on. Does that make sense now? Good. So there's 2 more of these. So they're PC relative and pseudo addressing. And so this now tells you more about what I was describing a little earlier with this PC plus 4. So that instruction that I was describing to us of 18, so that's 18 times 4, right? That instruction we had. So that's the value that comes out of the program counter. The program counter adds 4. This is it's just 4 with quotes around it. It's hard coded. It's a 32-bit value where the last 3 bits are 100. And then this comes out. Right? And so we have our 32-bit instruction. We're going to do sign immediate, sign extension, just like we did before. So what this is this is 16-bit value coming out of the instruction. Sign extension to 32 bits. That's sign extend. So now we have 32 value. And this is SL2, shift left 2. So now we're taking the value from the immediate. We're concatenating 16 bits, and then we're shifting left by 2. So we get that base addressing multiplied by 4. And then there's an actual adder physically in there. And this calculates, this is actually how branching works. So this is a branch instruction. So PC relative, we define formally as the branch address is the sum of the program counter and a constant in the instruction. So we've taken this constant in the instruction, we've sign extended it, multiplied it by 4 using shift left, and then we've added it, and then we go back to the instruction memory via the program counter. And then last but certainly not least, pseudo direct. Pseudo direct is jumping. So if you recall from we had R-type, I-type, and J-type, right? And J-type instructions were opcode and this 26-bit value. And I told you someday I'd tell you how this goes from 26 to 32. Yes, no, you're like, oh, we were dreading that day. Oh, no, please don't do it. Please don't tell us. Well, this is how it's done. All right, so again, PC plus 4 comes out here. So we have our opcode, 6 bits here, and then this is the 26-bit value. 26-bit comes out. And the first thing we do is shift left 2. So now we multiply by 4. But we keep all the values, so now it becomes 28 bits. So that's why it says 26 here and 28 there. So now this symbol, does anybody know what this symbol means? It's a circle with a dash down the middle in circuitry. No. Not a switch. This is what's known as, one more? Capacitor. Yes, definitely not a capacitor. All right, this is what's known as concatenation. And what this means is, in the definition here, it is concatenated with the 4 most significant bits of the program counter. Now, in the architecture you will be designing in your code, you're going to have 496 bytes in your instruction memory. So 496 is not going to get anywhere close to 2 to the 26. Because this is actually just 2 to the 12. So what that means is we're taking the 4 most significant bits from the program counter and we are concatenating them to the front of the jump instruction. So what that means is when we come out of here, we now have a 32-bit value. So let me describe concatenation a little further. So let's say I had a 6-bit value, right? And then I have some sort of 3-bit value here, so 101, right? And so this is going to be my new value. So shift left 2, actually let me make this. So shift left 2 becomes 10100. And then if I wanted to concatenate the 2 most significant bits, I would just put them here. So it's the exact opposite. We're doing the exact opposite of what we were doing back when we were doing restoring and non-restoring division. Remember we took the most significant bit of the result, flipped it, and made the least significant bit? We're doing the exact opposite. We're putting it in the front. So 6.3, you will definitely see this again.
What is that under program counter going into the
P4, this right here, that's a hard-coded 4. So it's 32 bits where it's 0, 0, and then the last 3 bits are 1, 0, 0. That's just hard-coded in there, and it's added 4 every time. So when you code this, you can just have an array with all zeros and then 1, 0, 1 at the end. It's 32 bits long. And you take an adder, you just take the value of the program counter and add it. So these are all design flows. You can use this not only on an exam and a quiz, but to be able to actually, oh hey, this is how I should do this. That should be 26, shift left 2, it should be 28. So then we have a 28-bit array. And then I concatenate, so I take these 4 most significant bits, I use a for loop, 1, 0 to 3, and now I've got my 32-bit value. All right, so then I want you to actually code PC relative, which is this guy up here. I want you to actually go through and go, I want a 16-bit, I have a 32-bit value instruction. Grab me the 16 bits, do sign extension, give me 32-bit, show me you can, because you already have shift left logical done, right? So just hard code 2 in there. You have an adder already. You can take some value, you can designate it as the program counter. You know how to hard code 4. So a lot of these things that we're starting to build up on, you can now reuse in functions to be able to do it properly. And then 6.2, I want you to 6.2, I want you to do that. And so this little blurb, basically, we now discussed a number of times we have this concept of instruction memory and data memory and that they're separate. So the reason why they were separated in MIPS is because if you have just one block of memory, so each instruction, you're trying to get an instruction and then update a value, right? So you have to do some, but when we get into this concept of pipelining, where we have 5 instructions in the data path at any given moment, that means we have times where we're simultaneously trying to update a value and get an instruction. This is what's known as a control hazard. So what they did is they just said, let's just make them separate and just get rid of these hazards entirely. So that's why it's designed that way. But we will go into control hazards next section. So we've already designed registers, right? So I have the struct here for the register. I've also shown you how to do a struct for a byte. So I call it byte array, and byte was defined as 8 is a pound define. So I have SRAM cells for bits and byte. And then we had already done this in section 4. We did this code for initialized registers, right? So you're reading in from a file, and then you're updating all 32 registers from that file, right? So you're going to do the same thing. And it's going to be very similar, a lot of similar code. Initialize instruction memory and initialize data memory. The difference is you're going to have different files. So you can have instruction.txt represents the instructions. So you can see here I've broken it up into bytes. So this is where your byte addressing comes into play. And your codes, I'm going to provide a file for you that's going to have, for instruction memory, it's going to have 4,096 bytes here. And then in data memory, it's going to be 512, so that can provide it for you. Or you could write your own code that will generate it. I might make that an extra credit question. So either way, you'll have the file available to you. So you can either earn points or you can not earn points. So 6.3 and 6.4, basically I'm saying I want you to design, that's right. So instead of 1,000 instructions, I reduced it to 64. And we're still gonna have 512 8-bit values in memory. So 6.3 is instruction memory, 6.4 is data memory. So you kind of go back to those same coding principles. You can call you just change the name of your file from registers to instruction memory.txt, and then or data memory.txt or dm.txt, however you want to do it. And then just show me that you can read values in. This is what it's going to look like. I've actually kind of done an example here. Remember in data memory, the one thing I want you to design is your file format's going to look like this. But I have 0, 1, 2, and 3. So when I have a function where I want to get a value from data memory, how would I want to do that? I have some sort of 32-bit number coming in. So let's say that number is 4. What do I want to do? All right, so first things first, I have 512 8-bit values in data memory, right? So I have a 32-bit value, but what is log 2 of 512? 8, right? So I only need to read the last 8 numbers. So you don't have to iterate through the first 26. You just go through the last 8, and then you go through the last 8, and it says, right? So you figure out what it is. You get 4, and then you go, and now I have this number 4. So what do I want to do to get a value from data memory? Christian.
What?
That's why I asked. So, data memory. I want to get a 32-bit value out. We're using byte addressing. I have the number 4. I figured out that it is the number 4. So, how do I get a 32-bit value out if I now have my pointer? I'm pointing at the 4th block.
Did you shift and no? Okay, that's good.
Any ideas?
You have to get your value.
No. This is machine code, hardware.
Oh.
We're talking about what the ampersand is doing, but I'm pointing to a value, a physical value, in data memory. I'm putting a value 4. Value 4 could be this guy, right? But I need a 32-bit value. What I've been harping on about these load word and store word instructions.
Multiply by 4.
Why? This is where now we're learning why. Any ideas why? Why do I have to multiply by 4? Yes. So I want this one, I want this one, I want this one, and I want this one. I want these 4. So you can figure out it's 4. They give me 4. Most significant, 8 most significant bits are 4. Next most significant bits are 5, 6, and 7. So give me those 4 8-bit values, put them into one 32-bit value, and return. And that is physically what a load word and a store word instruction is. So we have a couple minutes left. Ooh, this is a good place to end. All right, so the question you might be asking is, why do we want to do byte addressing? This homework assignment is going to be easy, 6.1 through 6.4, so I expect a lot of creativity attempts this time. I think I only got 1, right? So 6.4, are you guys familiar with this concept of the principle of locality? One, okay, so that's not bad. So principal locality is a program tends to access data that forms a physical cluster in memory. So multiple accesses may be made within the same block. So that's one of the reasons why in the problem we had the 7 elements of the array, and then I selected the 8th one. So I wanted to keep all the elements of the same program close together. And so as the compiler tends to put stuff into data memory, everything kind of gets closer and closer. And so there's 2 types of locality. Time and space, for you Doctor Who fans, right? Temporal locality, if an item is referenced, it tends to be referenced again soon. So if I want something, remember we're updating first over and over and over again. We're updating second and some. Something tends to be referenced, we're going to need it again. It just makes sense because you're going to have a lot of stuff into your memory. And then spatial locality is space. If an item is referenced, items whose memory addresses are close by tend to be referenced soon. So if you're accessing something in an array, odds are good you're going to be accessing another element of the array, right? So in our code, we were actually incrementing first, because every time we went while, we were incrementing +1 to be able to get that. So that allowed us to go through all the different elements in the array. So that's spatial locality. And then, last but certainly not least, we're going to talk about this concept of memory hierarchy. So we'll do 6.5, but then we'll drill down into what memory hierarchy is next class, next Tuesday. So memory hierarchy is a structure that uses multiple levels of memory in order to improve memory access time. And the memory hierarchy takes full advantage of temporal and spatial locality. So if the homework's simple, it's going to be 6.1 through 6.5. And remember, there's that second creativity challenge. I would highly, highly, highly recommend you try it because first and foremost, I'm going to be posting all your solutions on Blackboard so that I can help you. And you might see it on the exam, and you might see it a lot sooner. Right? Yeah, so I'd highly recommend you try it. Yeah, so are you guys now starting to understand my little hints? Okay, good. Usually about third way through the semester, everybody starts getting, oh, okay. Hey, that's why things count more later in the semester, because you guys figure out how I teach and how I grade. So, all right. In that case, since it's 10:45, does anybody have any questions before I dismiss? All right, then you're free to go.